Good morning, my name is Osvaldo Ascour. Today we are going to present this hydrodynamic zero-order flotation model. I work for OSB Digital and I'm a consultant fellow for SEEQ Advanced Analytics. Today's agenda, I'm going to introduce the integrated comminution flotation water recovery optimization. We are going to look at the advanced analytics infrastructure for dynamic decision support in mineral processing plants. We are going to discuss briefly what is called the fourth step to maximizing the flotation metal recovery. And then we are going to introduce the zero-order hydrodynamic flotation model, which we have available for several years now. And then the importance of the particle size distribution management in the grinding circuit, and then the management of the hair holdup profiles based upon turbulence and profiles of power, frother, air, and flotation levels, the flotation cell levels. And then we are going to look at this digital plant operation model as a process identification for the whole plant to improve the recovery and reduce the operating cost. And then we are going to look at some results and conclusions. Basically, the grinding flotation recovery optimization is defined by the whole chain supply being stable. As you can see here, the first thing that we need to do is to get those blue bars improved, because that's when the whole stockpile is working fine, the grinding is working fine, then the flotation is going to work fine, and we can continue to the thickening. The most important thing here is the size distribution that we create at the stockpile, and then the product of the grinding mill affects tremendously the recovery in the flotation. So if we grind too fine, we are going to have slimes. This is going to probably change the rheology inside the cell, and this is being noted because the fine particles don't get attached very well unless you have the right turbulence. And then the other part is that if we grind too coarse, this has been known by many years ago, is that if we don't have the right liberation, and at the same time the coarse particles do not attach strong enough at the with this 1 millimeter bubbles, which is the traditional average in a flotation cell, traditional flotation cell. So we need to really manage not the P80 as always has been done, is really the particle size distribution at the feet of the SAG mills or at the feet of the comminution, and the product of the cyclone output of the grinding circuit has to be perfectly defined, is possible with the right percent solid and the right mineral density. So for these things, what we collect from the process control systems has to be clean, sorted, and classified correctly according to the operating condition of the stockpile, the grinding, and the flotation, especially the rougher flotation. The same thing applies for the other cleaning and thickening of the concentrates and the tailings. But the most important thing is that we need to have these events on how the units are operated in general. So that's what we call it, the digital twin these days. And then we have that so we can aggregate the right data into information to create these insights. Once we have this information, forma behind the information means shape. So when we have the right shape of the data, we can really create insight and create analysis and advanced analysis to have the models created so we can see and understand what's going on and how we can improve. The first step is to organize the data sets into units and inventories using a template so we can have very easy access to the data. And the first thing that we do is that we characterize the operating conditions so we can analyze the hidden losses that are happening in the plant so we can smooth the operation and coordinate from the very beginning to the end so everything is consistently operated. We can aggregate the data at the different operating ranges. We call them capsules, and then we can visualize them and make sure that those are operating correctly before we start doing any modeling. When we do the modeling, we use the capsules to capture that information to generate the predictive models, first of all, for avoiding downtimes, and also for identifying the recovery and the grind cut or the grind size distributions. And then we have to deploy that, and then we are going to see how those deployment has to be done. The key thing is to have a very clear objective on what you are doing these projects, which is maximizing the yields based upon your projected planning and planning of the mill. And then the key is to, when you are not at that yield that you wanted to do or recovery that you need to do, you are going to probably be wasting energy and water. When you want to capture those at the second step, that is very well done, and we have many customers which are applying it for many years now. So we take the process flow diagram and we organize this top-down approach by looking at the homogenization of the plant, the whole grinding circuit with your feed and your product, and then we can manage that so we have the right product into flotation and then the right product into the thickening. So these are the first steps that we usually do, and then we continue with the next part of the mill. And then what we have been doing is that we see that there is a lot of opportunities to start the comminution at the blasting, and then we go back into the mining, and that's some of the experiences that we have been having with Barrick Gold and with ArcelorMittal. So we are going to look at that if we have time in this presentation. So the first thing is to transform that. If you have the PI system, you develop this cookie cutter approach, and then you put this into what's called SEEQ, which is the advanced analytics, to equalize, as you can see here, all the units with the right algorithms to really assess what's going on in the whole plant. This is the simplified version of the, as you can see, there are 5 objects. I'm simplifying it, but most importantly is that the crushing and grinding has to be very well set to get the right flotation. Here I'm putting the flotation in red because usually the grinding is not correct for the best flotation, and if the grinding is not best for flotation, it's also not good for thickening, and that's where we lose a lot of water recovery. And of course the tailings also suffer because it's really about 99% that is going into the tailing, and we are just recording a very small portion that goes into the concentrates. So what we do to stabilize this is that we measure all the energy consumption, the flow of the pulp through the plant, and also the water. These 3 variables plus the operating condition enable us to smooth the operating of the plant. For this, we need to have the right software, so we start looking at this SEEQ cortex that collects all the data from the different historians, from your lab data, from your mine data, and that gets organized without touching the original resolution, and we transform that data into information using Workbench, where we can document exactly what was done for every unit and how you were transforming, calculating the first derivative, second derivative, put the right filters. So we have a good set of clean information for developing the models, and also writing the reports based upon the results that are happening, so people can see and management can be connected to it. We have discussed that in another paper called Digital Transformation in the Mineral Processing and Extractive Metallurgical Complexes. I'm not going to go into much detail, but just showing you that you need to have the proper tools to do the online modeling, and also to present that to management so management can come back and then improve by working together with engineering, maintenance, and operations. And then also you can even move forward and do a lot more analysis when you have information to go and look at the whole plant by using the new Python algorithm that are becoming available. So the first thing is that you have to capture the type of material that is coming to the plant, and you can see here very clearly when you got changes in the pyrite content, the density changes, and also the recovery fluctuates quite a bit. And this is reported from a production perspective that you have instabilities in all the units, starting from the crushing, grinding, uh, flotation, and so on. These are all the units that needs to be synchronized correctly, and you have the energy wasted when you are not matching with your plant schedule. And the same is the water. So energy and water are the most important consumables that we are tracking to identify the hidden losses in all these processes and all these units in a mineral processing plant. Then the next step was really to identify these hidden losses and problem that we have in general. And if you can see here, if you don't have the right size distribution, not only is affecting your grinding, but also the flotation cell gets accumulated material. As you can see here, this was reported by Maron and Ciroulis at the Prosemin meeting in 2013 for Kennecott. So when you got those issues like that, the system is going to recognize those bad times, and those are when you are losing money. And we calculate those here by looking at the losing of the times and documenting everything, how you are transforming that information and developing the models to really predict the key variables that sometimes the measurements might not be good, but then you have to cleanse them and filter them correctly. So now we can start predicting the grinding by looking at the size distribution coming in, the size distribution coming out, and assessing what is for this particular size distribution that you will optimize your rougher flotation. You can use Optimill to really assess what are the waters and what are the rate, the maximum rate of grinding that you need to have for the SAG mill and the flotation, the pump and the cyclones, so you can maximize your throughput while you are maximizing your copper recovery at the same time. We are going to use the dynamic flotation model here. Dr. Firstenow in 1999 put us here with Dr. Herbst on top here, very close, because we have been able to create this model in 1982. After that, I've been working on that all my life and improving all the algorithms that are behind this dynamic simulation model, and now we are applying it, as you can see here, onto the real rougher flotations, but basically is based upon my kind of Firstenow, and we are going to go and describe that a little bit now today. Basically, the flotation inputs and outputs are very complicated. We have fit characteristics that are coming from the grinding. Most importantly, here we are going to be featuring all the hydrodynamic characteristics of the flotation process by having the right amount of air, the right amount of turbulence, which is generated by the kilowatt hours of the impellers, and also the level of the flotation cell. Those two things represent the turbulence in the system. So, and then we can predict your pulp flow rate and the concentrate flow rate in real time by performing specific mass balances using a very powerful gross error detection algorithm that enable us to do that in real time. And then we have all the hydrodynamic parameters, which is the entrainment of water, the drainage of water, the pulp hair holdup fraction in the pulp and in the frother, characterizing the pulp air interface, which is very nicely done, as we are going to describe, by defining the shock wave that is characterized in these two-phase flow vessels. Same as you do in the thickeners, same as you happen in your cyclones and solvent extraction plants and things like that. So the key thing here is this Dynaflote is basically formulated with three fundamental laws. The most important one is the model of the continuity equation that we assessed early on in 1976 with Fernando Concha at University of Concepcion And then I updated that with some additional results that we did some experimentation. And in 1991, I wrote that paper at the request of Professor Tiller to be able to expose that knowledge internationally. That equation is very powerful because it tells us that these two flows create an interface generated by the shock wave between the air and the pulp. And this is characterized by some equations that I'm not going to go in detail, but we are going to formulate today and present you some of those concepts that have been presented, but never in this way. The Kolmogorov turbulence theory is very, very important because that's how we really characterize the entrainment, the drainage. We characterize the attachment, the detachment that is happening in the most of the subprocesses that are happening in a flotation cell, and we're going to use the separation and modeling that Mike and Furstenau conceptually presented in 1968 at one of the International Mineral Processing Congress that we use and we adapted, and I parameterized with Kennecott data in my thesis in 1982, and this was also presented in the International Mineral Processing Congress in Toronto, Canada. So this is the model basically in a generic way. We do in a mass balance, population balance, and the key things though is the water balance is given by these two equations, which is the discretization of the hyperbolic equation that I just presented of the two flows, two-phase flows. And here we have presented this several times. The first one was in Toronto and in my thesis in 1982. After that was in the IMPC in Rome in 2000, 2005. We were invited to present this with details at the Century flotation due to the importance of this model. And then we presented the SME book on separation technologies. And then in 2018, I presented again at the IMPC in Moscow, where we really were able to have a lot of industrial results that were finally available, because before we find out that most of the time the power was not available or the air was not available, and there was very poor instrumentation. But when you got the instrumentation, we were able to test this very well. Importantly here is that we can predict the entrainment of water, we can predict the bubble size, and most importantly is the air holdup that we have found that is very critical. As you can see here, we have the turbulence represented by the power divided by the volume of pulp. Here also the same. So this turbulence and the measurement of power is very, very important to stabilize the way that the bank is happening. And this is the return rate of water based upon the Reynolds equation. You can read that on our paper, and also the characterization of the air holdup of the froth, which we model based upon this other equation. This is the exit on the concentrate. The amount of water is proportional to the amount of air, of course, that is calculated with this equation that we have been able to validate over the years. So this equation defines the dynamic volume balances that represent the continuity balance of the two-phase flows in these flotation cells. This is the attachment defined by Kolmogorov's theory, very elaborate result by Schubert and Bishop-Berger, and then those were included in my thesis, and we were able to characterize, parameterize it, and it has been very, very strongly defined. This has been also presented very recently in iPad, because now the computer power of these machines is enormous, so we can solve all the many differential equations here in real time and identify and show you the effect of this, as you can see here, this level, and you can see the model on sub-processes, all the key parameters being identified, and also the trends on how you are manipulating the amount of air, manipulating your power, manipulating the tailings, which is the most important variable. And when you touch the screen, you can see this other screen, and you touch the other way, you can see those. So those things you can experiment with them. And this is basically when you can do and see that you can end up with a full of froth if you want to, depending on the second order, this zero order process, which is very, very interesting. So that interface is characterized by the two-phase flow, and it's very interesting to play around with this because it's like a game, but you learn a lot and you can define your controllers and you can define what you can do. You can play with the parameters. So it's a very practical way to learn about flotation. If you want to model that bank, you just put several of these in parallel, in series actually in this case, and you calculate all the concentrates depending on the different species. And I'm not going to go into the details of this detailed model, but how we are solving this in the industrial practice. In the industrial practice, what we do is that we take the events of the type of ore and we do the grinding, we define the particle size distributions, and then we identify the state of every piece of equipment so we can assess when to use the model, when to do the prediction, and when not to do it, because if it's not working correctly within the windows of operation that are consistent, it's impossible to predict anything. Same would happen with an instrument or anything like that. And we calculate also the consumables. That was presented in another paper which defined the hidden losses. Today we're concentrating on how to predict the recovery and the grade and things like that. So what happened is that the P80 has been always being used, and we believe that that's not a good number. It's really the size distribution that really creates the right management of the flotation. And of course, when you want to do that, you get one size which is related to flotation because of the agitation that you need and the mixing that you have. And the other one is when you want to push your throughput. But when you push it too much, you don't do a good job, because actually not only you're damaging your flotation, but also you're damaging the valve of the flotation as we presented. And that's something that we need to be very cognizant that the business P80 or the business particle size distribution is what we need to aim at. And you have to do that in an adaptive way in real time. You cannot be doing that just once, like here, like this person from Kayawasi reported. You have to do that in real time. So we have been able to do that by characterizing the particle size distribution shapes that are now possible, and also because we have very sophisticated grinding models, we can do that depending on the type of ore and getting some of the georheology that is available today. I was very blessed to work with Professor Free at Duval for many years, and actually 5 years that we did a lot of work together. So that was extremely good, because I embedded those into the dynamic models of grinding, as you probably have seen them. We presented that I believe in 86. We wrote about that, but after many years of toying around with the data. This is showing one of our recent work where we are presenting the Godin-Schumann distribution plotted. So this is what we use to identify the right amount of waters and the throughput of the mill. So we need to have this difference going on in real time to maximize and to characterize correctly the product of the grinding to flotation. In the flotation, once we have this set of data coming from the grinding and from the mine, we can assess the model and we can characterize the profiles that are required here by measuring the power, the level, and identifying this level perfectly, so we have the right power intensity in each of these reactors in series. And the airflow rate, of course, has to be managed correctly, because it's influencing tremendously the amount of bubbles that we can have through the bank. Plus today we got also the cameras that are helping us to characterize the drainage that is going on from the top. So we have that in my equations that really predict very nicely what kind of drainage is going on by adapting the dynamic model to online model. These are the type of data that you see. You get data that is Gaussian, some data that is very complicated, and no, it doesn't move too much. So that's how you start doing all the machine learning that is required, and characterization of the feature variables for your target variables to be able to be modeled. This is an example using the SEEQ environment where we put our calculated recovery here, and then we can predict the recovery based upon all the variables that we are listing here, the particle size distribution in the feed to the flotation, the cyclone product, and the particle size shape of the product here. So very important variables that we characterize these days. This is really after cleansing, classifying, and making sure that everything is validated and ready to go, and the model works fairly well, and we can understand how to maximize the recovery in a line, in a mineral processing plant. And also we can enhance the control of the grinding circuit by having this soft sensor, very robust, that we have been using since I implemented the first time at Cerrita in 1984. So this is something that has been going through the years and becoming better and better and easier to maintain and easier to improve our grinding characteristics. This is also now by looking at this table, which is all the variables that are happening in each of the cells. This is using an Autotech environment. Not only that, we can calculate the losses, we can calculate the recovery in real time, and we can calculate the hair holdup to maximize the productivity as much as we can according to the grinding. The grinding is really the factor that needs to be integrated with flotation, and in some cases that's not done, and that's why you get these lower recoveries. This is basically, as you can see, that's the bubbles. The bubbles, we are seeing them in real time, but we need to understand them, and the way to understand them is to use them very deep learning machine algorithm that we got today. You know that when you get to a phone, it'll identify your face, where here you look at the froth and it will identify if the froth is good, what is the type of froth that you need, and you can download or characterize those bubbles and really infer tremendous amount of information about the behavior of your flotation today, things that you could not do 3 years ago. This is really what we can do now that we got all the feature variables for a mineral processing plant, and we can really see where we can move. And the other thing is that we are characterizing all the constraints that we have for every type of ore, starting from the homogenization of the stockpile and moving. So as you can see here, we have names that you don't recognize very well, like particle size shape of your primary grinding and tertiary grinding, and the profiles of your holdups and profiles of air. So these are variables that we put into this sophisticated environment using Python by using very nice information, not really the real data. It requires a lot of cleansing to get to this point, so this is not something that you do in one day. This is some of the applications that we have been able to do, and using this concept was in ArcelorMittal, where really they are making a lot of money. In this case, it was not flotation, I will say, but it was the gravity separation that is used here. The particle size plays a big role there, the viscosity and the densities of the material. Here we went back into the milling, into the mine, and to the blasting. So it was a tremendous project that we did there. This is one in Barrick Gold, where we did more sanitization and increase of the gold recovery. To start, to summarize here, the digital mineral processing model start at the blast. That's something that I don't have time to do today, but I'm reporting that because we are going always, when I finish doing the recovery model, we go to the blast, and we can improve the blast by measuring the recovery. So that's what is important here. The blast defines the recovery. Very important. So the P80 is not the right control variable. The particle size distribution shape is much better by using this hybrid simulation model in real time, and also the Godin module that enabled us to understand the two slopes on the grinding circuit, and really assess what we need to do. The operational flotation model includes the grinding disturbances, as you just saw there in my presentation. It includes the turbulence measures that we have for every flotation cell, and we use that as a specific energy consumption that drive the overall recovery. This generates the right error holdups profiles that we can calculate in real time, and we can manage that KPIs to tune the flotation ban correctly, to looking at in real time at the losses of copper, the recovery based upon the profiles of air, and the most important thing is the right size distribution. A dynamic decision support model is a requirement now for maximizing this overall mineral processing profitability, and this is due because we are running with plenty of power, since most of the time we have been able to implement this in the cloud, especially now that we have been in the COVID environment, been toying around with these models and doing things that we were never able to do before. So we are in a new digital era. This is a very important thing that I'm saying. We are using mostly the Amazon technology and also the Azure from Microsoft. So increasing the visibility of known is possible to improve the overall efficiency and sustainability in the mineral processing plants. This is my presentation, and thank you very much. My name is Osvaldo Pascur again. I work for OSB Digital. I'm a consultant fellow for SEEQ. So you can check these websites and let us know if we can contribute and be partners or coaching in your plans.